Good afternoon, welcome to my channel. My name is Don, my call sign is KE5ADX, and I am the RF Field Tech. Today I'm here to discuss Coax. I know other YouTube channels, they always talk about what radio to have, what kind of antenna to have, what the best radio, DMR, YSF, whatever. But really, you can have the greatest radio, you can have the greatest antenna, but without that coax in between and it being made properly, it being having the correct connectors and everything, your transmissions just won't get out. So let's start today, and let me go ahead and get all this out of the way as well. If you like this content, give me a thumbs up. If you smash that subscribe and the notification bell so that you can be updated every time I put something out. So without further ado, let's get started. Coax. Coaxial cable has a single copper conductor at its center. I'm going to go over the basics of it. It has a plastic layer that provides insulation between the center conductor and a braided metal shield. The metal shield helps to block out any inside interference from fluorescent lights, motors, and other computers, or just about anything. Your outlets, your wall warts. If your connectors and your coax are made correctly, then it'll help block out all that. Also, if you make it correctly and you weatherproof it correctly, it'll keep water and everything else out and help improve your transmission. Although coax cabling is difficult to install, it is highly resistant to signal interference. In addition, it can support greater cable lengths between network devices than a twisted pair cable. Two types of coax cabling are thick coax and thin coax. For the most part, we're going to use thick. The thin coaxial cable is also referred to as thin net. It's a 10-base-2, refers to the specifications for thin coaxial cable carrying Ethernet signals. The 2 refers to the approximate maximum segment length being 200 meters. In actual fact, the maximum segment length is 185 meters. Thin coax cable has been popular in school networks, especially linear bus networks. Basically, this is your RG6 for your home cable, your cable modems, stuff like that. That's this thin, your thin coax is what you use there. For the most part, we don't use that unless you are looking to do. You can use it for digital modes if you can make the connectors correctly. Thick coaxial cable is also referred to as thick net. It's a 10-base-5, which refers to the specifications for thick coaxial cable carrying Ethernet and RF signals. The 5 refers to the maximum segment length being 500 meters. Thick coaxial cable has an extra protective plastic cover that helps keep moisture away from the center conductor. This makes thick coaxial a great choice when running longer lengths in a linear bus network. One advantage of thick coaxial is that it does not bend easily and is difficult to install. Or disadvantages, not one of the advantages. You really don't want something that's hard. Primarily, companies that make this, and I'm not sponsored by any of these companies at all, so I don't get any money from them. CommScope makes some really, really great coax cable that is guaranteed for life as long as the connectors are made by one of their engineers. It is guaranteed against water incursion. They do have some that can actually make a full 180 degree bend. That is going to be their Superflex model. And that's just something, if you want to look into that, that's something you can do. Otherwise, you have Times Microwave. I use a lot of theirs. I specifically like their LMR 240 and their 400. It's just something I use at work a lot, so I'm kind of partial to that. I'm sure there's hundreds of cable makers out there. You can look into all of theirs, and at the end of this, I'll also tell you what the best coax for your radio is, believe it or not, or I'll give some suggestions of what the best for your radio is, and it's going to surprise you. It actually will. So the best coaxial cable impedances in high power, high voltage, and low attenuation applications were experimentally determined at Bell Laboratories in 1929 to be 30, 60, and 77 ohm, respectively. For a coaxial cable with air dielectric and a shield of a given inner diameter, the attenuation is minimized by choosing the diameter of the inner conductor to give a characteristic impedance of 76.7 ohms. Most of our amateur radios look for a 50 ohm. We use 50 ohm cable with balins, ununs to connect up to if you're using wire antennas, so that you can get that impedance matching. But according to Bell Laboratories, they say the best is 76.7 ohms. Even in cellular companies, they do 50 ohms. It is what it is. When more common dielectrics are considered, the best loss impedance drops down to a value between 52 to 64 ohms. Maximum power handling is achieved at 30 ohms. So if your entire coax run is at 30 ohms, you are getting maximum power handling. So 30 ohms are better, so 30 to 64 ohms, you're going to get maximum power. Anything below 30 ohms, you're going to start having some degradation in your line. The approximate impedance required to match a center-fed dipole antenna in free space, i.e. a dipole without ground reflectors, is 73 ohms. So 75 ohm coax was commonly used for connecting short-wave antennas to receivers. These typically involve such low levels of RF power that power handling and high voltage breakdown characteristics are unimportant when compared to attenuation. Likewise, with Cat5, although many broadcast TV installations and cable TV head ends use 300 ohm folded dipole antennas to receive off-the-air signals, 75 ohm coax makes a convenient 4-to-1 balun transformer for these, as well as possessing low attenuation. The arithmetic, I can't speak today, between 30 ohms and 70 ohms is 53.5 ohms. The geometric mean is 48 ohms. The selection of 50 ohm as a compromise between power handling capability and attenuation is in general cited as the reason for the number. 50 ohm also works out tolerably well because it corresponds approximately to the feed point impedance of a half-wave dipole mounted approximately a half-wave above normal ground, ideally 73 ohms, but reduced for low-hanging horizontal wires. All of the components of a coaxial system should have the same impedance to avoid internal reflections at connections between components. What that is saying is that every component of your system, your SO239 on your radio, your PL259, your N connector, your BNC connectors, every single one of them should have the same impedance, and you can do that through test equipment, which we'll cover in another video. And you can test the entire system from where you connect to your radio to where you can connect to your antenna, and you can get everything in that line to be the same impedance. That way you can have maximum power output, maximum transmit, maximum receive, and you'll be just fine. Your SWR will be perfect. It'll be wonderful. And we'll also cover some ways to get some of that common wave voltage off of your line. Such reflections may cause signal attenuation, which will decrease your power and your transmission. They introduce standing waves, which increase losses and can even result in cable dielectric breakdown with high power transmissions. In analog video or TV systems, I know that's video and TV, reflections cause ghosting in the image. So when you're doing slow scan TV, you can get ghosting in your images. Multiple reflections may cause the original signal to be followed by more than one echo. If a coaxial cable is open, not connected at the end, the termination has nearly infinite resistance, which causes reflections. If the coaxial cable is short-circuited, the termination resistance is nearly zero, which causes reflections with the opposite polarity. Reflections will be nearly eliminated if the coaxial cable is terminated in a pure resistance equal to its impedance. Basically, if you want your system to run the best, you really need to make sure that all of your connectors are made properly. You need to make sure they are connected properly at both ends, wherever you have a break, whether it's at your SWR meter, it's at your amplifier, it's at your radio, it's at your antenna. If you just run to a if you run to the base of your tower and then you have another line to run up your tower to connect up to your, you want to make sure that all of that is connected right, to make sure it's made properly, and that way you can minimize as much reflection in your line as you possibly can. So that's pretty much what I do at work. My job is to make sure that all of the resistances within reach that I can reach, which is usually everything on the ground, is at near zero reflection. I do that with a wide variety of test equipment. Some of it is way outside what I'll ever pay for myself. And this ensures that we get maximum power out, maximum return. We have low signal to noise ratio so that we can get maximum data transmission as well, because that actually plays into it. So if you're doing digital modes, FT8, FT4, Whisper, all of those, if you can improve the signal transmission through your coax, you will improve your data rates. A lot of people don't realize that you can improve data rates through your coax line, and that's part of my job. So, what is the best coax for the radio you have? I said you're going to like this. You may not like me after this, but I'm going to tell you anyway. Read your manual. I, for example, have a 2-meter 440 Yaesu FT 7100M, and in the manual it gives me LMR 400, RG 127, RG 213, and it gives the impedances and the losses at 100 feet. Now my antennas aren't 100 feet, so I don't worry that much about loss, but I still want to make sure that those connectors are made correctly. And when they give those values in your instruction, in your manual, that you have to understand that is in a controlled test environment. That's not real world. So they have a laboratory where they have machines that make these connectors and make these cables correctly, where they can control everything about the connection, so that when they say that, okay, this is the loss on this line, that is in a perfectly controlled environment. Do I recommend you buy prefabricated cables? If you want. I personally make all my connectors. I am certified through CommScope as a connector. I'm certified through them to make connectors on all of their cables. I am a Anritsu certified master line sweeper, so I know how to check even with CommScope cables. We use Anritsu, JDSU, Viavi for our test equipment at work. These are high dollar items. I would recommend, if you want an Anritsu, some of the older models, the S321s, I believe they're the S321s. I've seen them on eBay for $350. If you've got that kind of money to spend, they will sweep everything from 1 hertz up to, I believe they'll go all the way up to 35 gigahertz. So that's the kind of test equipment you want. Go ahead. And I apologize for the fan in the background. That's an air conditioning unit. I apologize for that if you can hear it through here. Otherwise, read your manual. Your manual will tell you what the recommended cable by the manufacturer is, so that you can get the best transmission quality from your equipment. Like I said, I personally use LMR 240 because it's good up to 35 gigahertz. LMR 400, I know at work we use LMR 400 for everything up to 11 gigahertz. So LMR 400 is a good option. Problem is making those connectors. There's a lot of specialty tools. I'll get into another video where I show you what tools I use. These are my personal ones. They're not supplied by work, but I do use them at work. I will show you test equipment, how we test, what we test, and how we determine whether a line on the ground is good and needs to be remade or replaced, and how you can even use your test equipment to identify RFI, PIM. PIM is passive intermod, which can be caused by just about anything. A rusty gate that's in a field, rust on your tower can cause it. Your radio can cause it. Typically, we call that RFI. Industry standard now is PIM. They're the same thing, really. So I hope you would like this video. Again, smash the thumb up if you like it. Subscribe, and we'll see you the next time. 73s.